Good morning, everyone. Okay, a new day. So we will continue learn oscillations today, and we will explore more things about this kind of content knowledge. And if you have any question about like yesterday, you can like send me in the office hour or email me, text me. Yeah, that all works. And yeah, I don't know if you have already received my announcement and email. You need to re-enroll the mastering physics through the Blackboard. Otherwise, the grade cannot be uploaded to the block Blackboard from the mastering physics. I think that's my problem because I forgot I need to connect them firstly. Sorry about this inconvenience. And but if you have any questions about this part, and just let me know. Okay, let's begin today's class. And let me share my screen. Share. Okay, let me try to hide floating. Okay, yeah. Today we will continue talk about oscillations, and like there. Sorry. Um, oh, okay. And And like I mentioned yesterday, and for the chapter 40, we mainly focus on oscillations. And the main goal for this chapter, we like try to understand the systems that oscillate with simple harmonic motion. Do you guys remember how can we how what is simple harmonic motion? How can we tell this system oscillate with simple harmonic motion? Do you remember that? Yeah, like if you remember, if you try to remember that, you will know if the oscillate with simple harmonic motion, which means this oscillation move this oscillations move can be represented as a sinusoidal function. Yeah, do you remember that? Yeah, if this oscillation move can be represented as a sinusoidal function, we call it simple harmonic motion. Yeah, you can see there are some uh, you can see there are some examples. Yeah, there are some examples, and you can see this swing. If I pull the kid from the highest to the equilibrium position, and then to the other side of highest, it's just uh, from here to here, here to here, here to here. And if you observe the uh, move trees, it is just like a sine function, like all cosine function. And you can see the uh, I don't know if I mentioned that the sinusoidal function, it's just like it moves as a time pass, like the x-axis x-axis is the t, the time, and the y-axis is the move displacement, like a negative a, and from t, maybe it is just the biggest, and then try to, yeah, it's just like this. Okay, and yeah, you can see the clock is a similar thing. If it is move from here and to the equilibrium position, and then here, and back again, back again, back again. Yeah, and the metronome is the same thing. Yeah, and but do you remember? I also talk about one term called a linear restoring force, like that. Yeah, yeah, the move trains as the displacement like have as a time pass, it is just a sinusoidal function, but the force, like the restoring force, it's just like a linear relationship. For like we talked about yesterday, all the most not all like most simple harmonic motion, we can like consider like most simple harmonic motion as two different um, different like a oscillation move. Do you remember that? Yeah, one is like a spring, mass on a spring. Am I right? And the other is what? The other is pendulum. Pendulum. Do you remember that? Yeah, yeah, because you can see, yeah, this is just a pendulum, pendulum, and some is just like a spring. There is no angle change, but there is just the distance change. Yeah. Okay. Yeah. So like but the restoring force you can see the restoring force is just a linearable with a linear relationship with the displacement. Yeah, if you try to remember what we have already talked yesterday. Okay, this is like a simple harmonic motion. And let's talk about today's goal. And today we will review simple harmonic motion. And we will learn about energy in simple harmonic motion. I think you have already learned what is energy, uh, uh, and how to calculate it. And if you forgot it, and you can recall the chapter 10 and yeah, the chapter 10 to review this energy thing. And then we try to understand the pendulum motion and explore damped oscillations and learn driven oscillations and resonance. Many things, am I right? Yeah, but I will tell you what's the most important thing in today's class. And okay, let's try to review simple harmonic motion. Yeah, this this picture is very important. Synthesis like 41, like you can find this in textbook page 493. Yeah, uh those equations like describe the all the like variables we need like the this is displacement and this is uh, velocity and this is acceleration. Yeah, you can see when like a object moves, those three are what we want to know, like the position, velocity, and acceleration. And for all the simple harmonic motion, actually they have the same rule. And for the displacement, you can represent it using this equation. And for the velocity, you can use the equation, this one. And for the like acceleration, you can like represent it using this equation. And you can see this is like as the time pass, the axis is time. As the time pass, how the displacement, how the velocity, how the like acceleration change as the time pass. And it is, you can see it is a sinusoidal functions, sine or cosine, and it has a period, and which means it has some specific frequency. Yeah, and this is the maximum value. How to get the maximum value? I think I mentioned this in last class. You can see the cosine, the sine has a range. Yeah, because it will from -1 to 1. So which means 1 is the biggest value for this one, I'm right, for this part. So which means the maximum will be when this sinusoidal function is 1 or -1. This is the maximum value. Does that make sense to you? Yeah. So try to like remember this. Like if you want to describe all the simple harmonic motion, and you can use these equations. Yeah. Okay. Let's continue. Any question, just let me know. Okay. Today we will talk about energy in simple harmonic motion. You can see the like the interplay between kinetic and potential energy is very important for understanding simple harmonic motion. And I don't know if you guys remember what is kinetic and potential energy. if you don't remember it, you can like review the chapter 10 and to see it to review it like and try to understand that. And but here I tell you like a kinetic energy, it is obvious. Yeah, when object moves, the energy is a kinetic energy. It is obvious, I'm right. And the potential energy, which means it has some like a potential thing in the future. So which means even there is no like a velocity, this object doesn't move now, but it has some potential to move. So which means this object has some at this point it has some potential energy. For example, when this spring mass in like a horizontal spring and here like the velocity is what? Is zero, am I right? So, sorry, the v is zero, which means there is no kinetic, there is no kinetic energy, am I right? But you can see it is has a the like the big it has a big potential energy, which like this potential energy which make this object like runs to the left. Does it make sense to you? So which means if this like a glider, this object has a specific energy, yeah, you can see like the object always have like the like some in this in this like a movement, they have the specific energy, and the kinetic energy and the potential energy can be transferred with each other. You can see for this point, yeah, here this point, turning point, and the like there is the most maximum the maximum displacement, and you can see the kinetic energy is zero. There is no velocity, but the potential energy is the maximum. And you can see those two added together, it is a fixed thing. Yeah, does it make sense to you? Because in this moment, yeah, we just ignore the friction, yeah, between the glider and the floor. Yeah, this is an ideal like situation. So just ignore the friction. Yeah, so which means the kinetic energy and the potential energy can be transferred to each other, and the sum for those two is a specific value. Does it make sense to you? Yeah. Okay, let's continue. And yeah, like for mass on a spring, when the object is at rest, the potential energy, like here, sorry, yeah, is a maximum, and the kinetic energy is zero. At the equilibrium, yeah, here is the equilibrium equation, like position. The kinetic energy is maximum, yeah, because at this point, the velocity is the maximum, reach the maximum, which means the kinetic energy is a maximum, but the potential energy is zero. Yeah, this is just like a energy always keeps the same, like in an ideal situation. Yeah, doesn't make sense to you? I think this one is not difficult to understand. Uh, okay, and then the potential energy for the mass on a spring, we can use this equation to represent it. Actually, you can find this equation in chapter, also in chapter 10. And the spring, the like potential energy for spring is we can use this equation to represent it. And the conservation of energy can be written like this. Yeah, this is the kinetic energy, and this is the potential energy. Actually, those two energy add plus together, they will be a constant. Like I said, if you add this together, it will be constant. Yeah, it is always the same in an ideal situation. Does it make sense to you? Yeah. If you want to know how can we get why these two equations, you can review chapter 10. Yeah, like this is the equation for kinetic energy, and this is for the equation for potential energy. Okay, and for this moment, in this moment, and the kinetic energy and the potential energy, they add them together, and it is a constant. Yeah, because yeah, it will always oscillate continuously. Yeah. Okay. At maximum displacement, the energy is purely potential. You can see here uh, the kinetic, sorry, the kinetic energy. Sorry. The kinetic energy is 0, K equals 0, but the potential energy equal maximum, which means the like we check this equation, which means yeah, we only the like potential energy we have, and there is no like kinetic energy, which means we we can get this equation like the uh, the the energy is purely potential, and it is equal this thing. Yeah, because here the x, the displacement is the maximum. It's a and square. Yeah, and at x equals 0, you can see here is x equals 0. The equilibrium position, the energy is purely kinetic. Yeah, just when you like review this image, just pay attention. Sometimes the axis will change. Sometimes it is time, which means as the time pass, what is the like how the things change. But here it is as like a displacement change, which means the displacements from negative a, yeah, here from negative a to a, yeah, and how the like energy change, and x equals 0, the equilibrium position, the energy is purely kinetic. So which means this one we have for now the velocity is the maximum. So we have this equation. Does it make sense to you? Yeah. Okay. Let's continue. And let us like try to understand that using using a conceptual example like 40.5. Actually, you can find it in the textbook. Yeah, we can let's review this exact example. Yeah, this energy changes for a playground swing. Yeah, for example, you are at a playground undergoing simple harmonic motion on a swing. Describe the changes in energy that occur during 1 second of the motion, starting from when you are at the farthest forward point from here and motionless, and just to swing back to the motionless and then swing back. Yeah, like in this process from here to here to here, like try to understand like describe the changes as in energy. I think this is obvious. I'm right. Like the motion of the swing is that a pendulum. With you playing the role of the pendulum bob, the energy at different points of motion is illustrated in the figure. When you are like motionless and at the farthest forward point, you are raised up. Yeah, and your energy is entirely gravitational potential energy. Yeah, like in this point. Yeah, you are motionless, which means the velocity is 0, and the kinetic energy is 0, but the potential energy is the maximum. Yeah, your energy is entirely gravitational potential energy. Yeah, does it make sense to you? Okay, and as you swing back, yeah, sorry, as you swing back, and your potential energy decreases, and your kinetic energy increases because you have a higher speed, reach a maximum when the swing is at the lowest point. the swing continues to move back forward. Yeah, move back forward. You raise up, transforming kinetic energy into potential energy again. Yeah, the process then reverses as you move forward. Yeah, which means here you have the maximum potential energy, but no kinetic energy. And to the lowest point, and you have the maximum kinetic energy, but no potential energy. And when you raise up again continuously, and then you're this moment will transfer kinetic energy into potential energy. Yeah, and the process then reverse that as you move forward. Does it make sense to you? Yeah. Okay. Yeah, because this like swing, like I said, it's just a simple harmonic motion. Yeah. Let's try to think about more about this process. And this description matches the experience of anyone who has been on a swing. I think everyone has already had a swing before, am I right? And you can see if you playing with a swing, and the situation is just like this. Here, when you reach the highest, it seems to stop there, but then it will rush down to the lowest point. At the lowest point, you can see it's very fast. The speed is very fast until you reach the highest point, in your opposite side. Does it make sense for you? Yeah. So you know that you are momentarily motionless at the highest point, and that the motion is farthest at the lowest point. Yeah, if you forgot these things, you can find a way today or this week and try to experience the energy transferred from the potential energy and the kinetic energy. Yeah, you can try it. Yeah, I think that would be interesting to just a university student and play the swing with kids. That would be interesting, yeah, for you. Okay, let's continue. Okay, and let us try to finding the frequency for SHM. Yeah, because of a conservation of energy, the maximum potential energy must be equal to the maximum kinetic energy. Am I right? Yeah, because the energy should be the constant, and when it is the max focus the K plus P should equal constant. Yeah, and when the K reaches the maximum, which means this is zero, maximum equal constant. And if the potential maximum, which means this part equals zero, so it will make it equal constant. So which means those two will equal with each other. Does it make sense to you? So then from this equation, we solve this equation, and we can find the maximum velocity. Do you know how to resolve these equations? Yeah, let me show it to you. For here, 2m v max square equal ka square, and 2, and those half will be removed because have the same half on the both side, and then we will get mv max equal ka, and then the vma square equal k divide ma square. Yeah, which means vm max equal k ma. Yeah, we got this one, and then root this, and then we will get this one. Does it make sense to you? And you can see the K constant, the spring constant, and the quality of this object will always be the positive value. So we can use this equation, and this here we can use these equations to get the biggest the like highest velocity, the maximum velocity. Yeah, we know like V max for a small simple harmonic motion, the like a maximum velocity is also equal this one. Do you remember that? Okay, I think if you don't remember that, don't worry, and I will try to. Yeah, here. Yeah, this is the velocity. If for simple harmonic motion, yeah, we got these equations. And for the maximum velocity, yeah, just let the same equal one. Uh, yeah, like uh, same equal one, and then the maximum velocity will equal these things 2 pi fa. Um if you like try to find this, yeah, yeah, okay, understand that? Okay, let's continue. Here, okay, yeah, we have this equation. We also have this equation, which means those two will be equal with each other, which means root square will equal 2 pi fa, and that means f, we can get f equal what? F will equal, like we put 2k here, 2 pi here, and a will be, and then we will get 1 over 2 pi square root, like k divided up. Does it make sense to you? And then because t equal what? T equal 1 over f. So which means we just 1 over these things, and we can get this one. So like for now, we can get the frequency and the period of simple harmonic motion for mass m on a spring with spring constant k. Yeah, does it make sense to you? Yeah, okay. Like let's continue. Like we can make 2 observations about this equation. Yeah, about this equation. Yeah, we can try to observe it. You can see the frequency and the period of simple harmonic motion are determined by the physical property of the oscillator. The frequency, like what is the physical property of the oscillator? Physical property, which means it just decided by m and the key spring constant and the like a mass the mass m, am I right? The object mass. Yeah, so it's just determined by the physical property of the oscillator. Yeah, it will not like decided by like you pull up, how long you pull up this spring, how long you push that spring. Does it make sense to you? It's just determined by the spring constant and the object mass, which means if you use a specific spring and a specific object, like the frequency will keep the same always. Also the period. Does it make sense to you? So the frequency and the period of simple harmonics do not depend on the amplitude, like the displacement. Yeah. No matter how long you push it and you pull up, and that doesn't matter. It just depend on the like kinetic spring constant and the like object mass. Okay, interesting. Am I right? Yeah. Maybe yeah, you maybe you will think if I pull it a lot, I'll push it a lot and it will like move fast or move slow. Yeah, it's not like that. And like for the same spring, the frequency and for the same spring and the same object, it's the same frequency always. Yeah. Okay, let's continue. Okay, based on these things, there are some like quick check questions. Let us review that. Yeah, there are a set of springs all have initial length 10 centimeter. Yeah, this is the original like spring. The like original length is just a 10 centimeter. Each spring now has a mass suspended from its end. Yeah, there are some like mass like suspended from its end. And the different springs stretch as shown below. Okay, you can see here. Here and the different stretch as shown below. Now, each mass is pulled down by an additional 1 cm and released so that it oscillates up and down. Which of the oscillation system has the highest frequency? Yeah. Do you have any ideas? Yeah, if we want to resolve this problem, we need to like write this down here. So yeah, F equal what? Yeah, because we want to like uh to to know which system has the highest frequency. So the frequency is 1 over 2 pi root square k divided r. Which try to think about that. According to this equation, what we can get, which means if the mass for an object is smaller, the frequency will bigger. Does it make sense to you? Because it's divided. And if the spring constant is bigger, which means the frequency will bigger. Does it make sense to you? So like let us observe those four. Like firstly, we know we need to choose 100 gram. Am I right? Because if when the like mass object mass is smaller and the frequency will increase, and then from the A and C, and yeah, and I know you have already learned something about spring on chapter 8. We will know like the spring constant will be bigger if the spring is harder, like the harder the spring, the bigger spring constant, which means if the spring is harder to stretch, which means the spring constant will be bigger. Does it make sense to you? If you don't remember these things and you can recall, like review the chapter 8 and you will find it. Yeah. And which means the C has a bigger spring constant compare with A. Yeah, compare with this one. So what's the answer? It's obvious. Am I right? It's a C. Yeah, we need to like I will write the equation here. 1 divided 2 pi is a fixed thing. We never change. We will. It can be now changed by us. I'm right. And the m and k we can change it according to the physical like properties. And the mass, yeah, we need to choose a smaller one. So these two, and the spring constant we should choose the bigger one, the harder one. Yeah, this one. So the answer will be C. Does it make sense to you? Yeah. Any question, just let me know. Okay, let's continue. Yeah, let's see the another questions. Two analytical analytical blocks, two analytical blocks oscillate on different horizontal springs. Which spring has a larger spring constant? Yeah, which spring has a larger constant? The red one or the blue one, or there is no information to tell? Yeah, two identical blocks, which means two same blocks. Yeah, which means let us to see. Sorry, I will write it down 1 over d k. So yeah, let's see this, and this is which means t equal 2 pi mk, because two identical blocks, which means the m is same. Am I right? It's the same thing. We just don't think about that. So we focus on if we want to know the situation about k, and we need to know the t, am I right? So here, t or f. Here, let's just tell the t. And we know this equation, t equal to pi m divided k, which means t square equal square m, which means k equal m divide t square, which means if the period is smaller and the spring constant will be bigger. Am I right? So which one? This is the period for the red one, and this is the period for the blue one. So I think it's obvious. We just need to find the smaller period thing. Am I right? So yeah, obvious. It is like it is A. Am I right? Yeah. Okay. And actually, if you judge from the frequency, it would be same thing. Yeah. If this t is smaller, which means f will be bigger, and the k and f has the same like when the f increase, the k will increase. It's a similar thing. Does it make sense to you? Okay, let's see the other one. Okay, block of mass M oscillates on a horizontal spring with period t equal 2.0 second. If a second identical block is glued to the top of the first block, the new period will be, like I said, we just t equal what? 2 pi m divide k, am I right? Yeah, so here we just t, the original t equal to, am I right? So for now, we just the key, the spring is the same thing. We just add one more mass, so it will, which will be 2, am I right? So which means the new t will equal like the square root 2 to mk. And this is the old t, am I right? So we equal old t, and which means it equal multiple the old one to. So what is this one? I think it's obvious, am I right? It is D. Yeah, does it make sense to you? Yeah, because the old one is 2, and the new one is just like we add a more mass for this for this situation. So we just the new t will equal the square root 2 multiple the older t, older period. Does it make sense to you? So we can easily get the new one. So you can see here. Yeah, we just use these equations. So try to remember these equations. Okay, let's see the other one. Yeah, we don't have the other one. Okay, let's try to identify and analyze SHR. Okay, and yeah, you also can find these things in the textbook tactics box 40.1. And let's review this review these things and try to identify and analyze SHM. If the net force acting on a particle is a linear restoring force, the motion is simple harmonic motion around the particle's equilibrium position. Yeah. Let me give you the point. Yeah, which means the net force acting on a particle is a linear restoring force. Like I mentioned in the beginning of the class, if the net force is a linear restoring force, like it has a linear relationship with the displacement. Yeah, and this motion will be a simple harmonic motion, and yeah, and the position, velocity, and acceleration as a function of time are given in synthesis 14.1. Do you still remember? Yeah, the first when I review the simple harmonic, I just give you those equations. Yeah, like for simple harmonics, and you need the position, velocity, and acceleration just can be represented by that like a sinusoidal function. The equations are given in terms of x, but they can be written in terms of y, u, or some other like a variable if the situation calls for it. Yeah, the like the equation are given in terms of x, like a displacement. Yeah, but you can write it in terms of like a y, u is some other. Yeah, like a it's a similar thing. Yeah, just like use different things to represent it. And the amplitude A is the maximum value of the displacement from equilibrium. The maximum speed and the maximum magnitude of the acceleration are given in synthesis 40.1. Yeah, you can see we just give you the maximum speed and the maximum magnitude of the acceleration. Yeah. You can review the synthesis like 40.1. Yeah. Okay, let's continue. The frequency f and also hence the period equal like 1 divided f depends on the physical property of the particular oscillator, but f does not depend on a like yeah, from this equation the f the t does not depend on like a displacement. It just depend on the physical properties. Yeah. And for a mass on spring, the frequency is given by these equations. And the sum of the potential energy and the kinetic energy is constant. As the oscillation proceeds, energy is transferred from kinetic into potential energy and then back again. Yeah, we have already talked about this a lot. And then let's review with pair if the okay, let's review the other questions like to improve what we have to talk about in this tactics box. And a mass oscillates on a horizontal spring with period t equal 2.0 seconds. If the amplitude of the oscillation is doubled, the new period will be okay. Try to think about how to represent the equal what? 2 pi k over m. Does it make sense to you? Yeah, because you can see f equal this one and t equal 1 divided f, so which will be 2 pi. And m, sorry, it will be m divided k. Okay. M divided k. Yeah, this is the equation for the period. So if the amplitude of the oscillation is doubled, the new period will be what? You can see the period is not related to the amplitude. Does it make sense to you? Yeah, so which means the period will keep the same. Yeah, it's still 2 seconds. Does it make sense to you? Because it only depends on the physical like properties. Yeah, the mass, object mass, and the spring constant. Okay. Yeah, it is 2 seconds. It will be keep the same. Let's check these questions. And a block oscillates on a very long horizontal spring. The graphic shows the block's kinetic energy as a function of position. What is the spring constant? Yeah, okay. Try to recall what we have already learned in today's class. We know like the let me the potential like energy. Sorry, equal U equal to 1/2 kx squared. This is the potential like energy. And for the kinetic energy equal half mass object and velocity square. And you can see here, we know the biggest, the maximum kinetic energy is hg, am I right? Yeah, which means the maximum what? The maximum potential energy is what? Yeah, we know like for like simple harmonics, the maximum energy, maximum like kinetic energy equal maximum potential energy. So like max, they equal each other because we want to get a spring constant, but the spring constant is only related to the potential energy, am I right? So which means if the maximum kinetic energy equal 8, which means the maximum potential energy is also equal 8. So which means 2.5 kx equal what? Equal 8. Am I right? And what is x? Here, the maximum should a, am I right? What is the a? It's 2. Doesn't make sense to you because the like uh, position when the position is 2 is reached to the maximum, which means the maximum displacement is 2, which means 2k4 equal 8. So which means k equal what? 4. Does it make sense to you? Yeah, because here 2 and then divide it 4. Does it make sense to you? Yeah. Just think about what we have already learned in today's class. Yeah, you can see here is the same thing. Yeah, the potential like energy, the maximum potential energy equal the maximum kinetic energy. And then we can use this equation. Oh, sorry. We can use this equation to get what we want. Yeah, does it make sense to you? Yeah, any questions, just let me know. Okay, let's check another one. A mass oscillates up and down on a spring. The motion is illustrated at the right. Yeah, illustrated here. Yeah, this is equilibrium position, and then lowest point of the motion, and the equilibrium position, and the highest point of the motion, and then equilibrium position. Okay, at which time or times showing is acceleration 0? At which time or times showing is the kinetic energy a maximum? At which time or times showing is the potential energy at maximum? Okay, let's try to think about that. At which times or time showing is the acceleration 0? Yeah, the acceleration 0, which means it should be in what position? Try to think about that. I will give you 1 minute to think about that, which means it should be in equilibrium position. Does it make sense to you? Yeah, because acceleration, which means it has already has if the acceleration reached to 0, which means it has already get the maximum velocity. Does it make sense to you? And yeah, which means it is A, where is the equilibrium position? A, C, E. Okay. And what time or times showing is just don't miss, just don't write A or C or E, just a single one. You can see you need to put all the equilibrium position here. Okay, at which time or times showing is a kinetic energy a maximum. Kinetic energy means it should reach the highest maximum velocity. Does it make sense to you? So which point is the maximum velocity? I just mentioned that like maybe 1 minute ago. Yeah, it also in like an equilibrium position. So yeah, you need to put A, C, E here. And which time or times showing is the potential energy at a maximum. Yeah, I think well, obviously the lowest point and the highest point. Yeah, so it is B, D. Yeah, does it make sense to you? Yeah, try to think about that. Okay. Yeah, this is the answers for this one. It's just the same as we talk about. Okay, let's continue to talk about one question. For different masses, a from, yeah, here, let's try to different masses hang from four identical springs, which means four identical springs with an unstretched length of 10 centimeter, which means the original length is 10, and causing the spring to stretch as noted in the following diagram. Yeah, which means this four spring is the same thing. Now each mass is pulled down by an additional 1 centimeter and released so that it always oscillates up and down. Which of the oscillating system has the highest frequency? Okay, let's try to, this one I think is easy for you. So what is the frequency? Try to remember that it is 1 over 2 pi square root what? Oh, sorry, it should be k. It should be k. Okay. Okay. I think it should be k divided m, which means the smaller one, yeah, because it's four identical spring, which means the constant is the same thing, am I right? It's the same value. So which means that the frequency now depend on the mass, which means that the smaller mass like have the bigger frequency. And so which one is the right answer? Which one is the right answer? I think it is obvious, am I right? It is A, yeah, because we use this equation. Yeah, and then we need to choose because it's four identical springs, so we need to choose the smallest mass. Yeah, it's this one. Okay, let's check another one. For 100-gram masses are hung from four springs, each with an stretch length of 10 centimeter. The four spring stretch as noted in the following diagram. Yeah, and now each of the masses is lifted a small distance, released and allowed to oscillate. Which mass oscillates with the highest frequency? Yeah, it's a similar thing, but yeah, you can see in this question, the spring, like four springs, it's not the same. It's not the identical springs. It's just four different springs, but the mass is the same thing. Yeah, so write down the equation for the frequency. What is it? 1 over 2 pi square square root square like k over m. Am I right? For now, as a k, m is the same thing. So the k, the frequency depends on the k, which means the biggest k, then the biggest frequency. That makes sense to you. So which one is the biggest spring constant? I think if you remember what you learned in chapter 8, you will know the bigger spring, the bigger spring constant, which means the spring will be harder. It's difficult to stretch. So which one is the right answer? I think this is obvious, am I right? Yeah, it is A. Yeah, because you can see this one is seem very difficult to stretch, which means it has a biggest spring constant. Yeah, does it make sense to you? Okay, let's try to review the other examples. Finding the frequency of a mass hanging from a spring. Yeah, okay, a spring has an unstretched length of 10 centimeter. A 25-gram mass is hung from the spring, stretching it to a length of 50 centimeter. If the mass is pulled down and released so that it oscillates, what will be the frequency of the oscillation? Okay, I think this one is not a difficult one. And the strategy is the spring provides a linear restoring force, so the motion will be simple harmonic. It's obvious. We have already talked about it late a lot. As noted in like a text box 40.1, the oscillation frequency depends on the spring constant. Yeah, because you can see the mass is object is a fixed thing, which we will determine from the stretch of the spring. Okay. Okay, yeah, I think these two has the same thing. And when the mass hangs at the rest, wait for a moment. Let me see. Okay, after stretching the spring to 50 centimeter, and the net force on it must be 0. Yeah, because you can see you stretch it to the net force on, yeah, on this situation. Let me see. On this situation, and the net force, like which this force plus this force is must be equal, because this is an equilibrium position. Does it make sense to you? Thus, the magnitude of the upward spring force equals the downward hit, which means these two force equal with each other. So, which means this is the spring force. We can, yeah, this is the delta. K delta L equal mg. Yeah, we have already learned in NASA class, which means we can calculate the spring constant equal like m equal, because m is 25 gram, it is 0.00 to 25 kilogram, and the g, yeah, is a constant value 9.8, and the delta L, yeah, we already know that, but we need to like transfer it to the meter, yeah, and then the spring constant we can get is this one, and for now we have the mass and we have the spring constant. Then the frequency is easy to get, I'm right, because we use this equation. Does it make sense to you? Yeah, like for this situation, yeah, this spring force and the like gravity force, actually it's equal, because it's like it's this position is just the equilibrium position, and then yeah, we access this one, like 21 hertz. Yeah, you can see the frequency is 22, but not 22, 2.2 hertz. 2.2 hertz is 2.2 oscillations per second. Yeah, this seems like a reasonable frequency for mass on a spring. A frequency in kilohertz range like would have been suspected, because it's still, and in this still situation, and like if the mass, yeah, because yeah, this one is because if it's kilohertz, it's so fast, yeah, like which means per second is just like a 2.2 oscillation, like this situation seems reasonable for us, not the kilohertz, like not like 100 like oscillations per second. It will for like a spring, it's too much for us. This one is more reasonable for us. Does it make sense to you? Okay, let's check this example problem. A 5.0 kilogram mass is suspended from a spring, which means there is a spring and one mass object suspended here, and in this position is position, and then pulling the in this equilibrium position. Do you guys remember what's the character, what's the features for this situation, for this position? Which means the spring force and the gravity force is equal. Equal. Those two are equal with each other, and the net force equal 0. Yeah, this is equilibrium position. And then pull this mass down like a 10, yeah, 10 like a centimeter. Sorry, it's not very accurate, but yeah, just like that. And it will takes a force of 20 N. What does that mean? Do you know? Do you guys remember? Do you guys know what does that mean? Which means if you like pull the mass down by an additional 12 centimeter, you will need more like actual force 20 N. Yeah, so which means here in this situation, in this position, the net force equal 20N. Am I right? And if the mass is then released, it will raise up and then come back down. Yeah, like this is just a simple harmonic motion. How long will it take for the mass to return to its starting point, 10 centimeter below its equilibrium position? Like, does any does everyone know what does this question mean? Which means like it ask you how long will it take for the mass return to its starting point, which means after you release, how long will it take for the mass to return to its starting point, which means it let you to calculate the period. Okay, the period is just like the frequency period. It's the same thing. If you know the frequency, and you will know the period. If you know the period, you will know the frequency. And for the frequency, there is like a equation, yeah, 2 pi k divided m, just like this one. And then the t equal what? 1 over f. So it's just yeah, is this like thing. Here, it just let you calculate the period. So which means you need to know for this equation, you need to know the mass for this object. Obvious, you know that, I'm right, it is 5.0 kilogram. And the other one, you need to know the spring constant. So which means like and then you can calculate the period. And for the spring constant, we know like here there is a net force equal 20N, like 20N, which means this spring stretch this long, it will like take a force of 20N, and we have this equation according to what? Which law? Yeah, Hooker's law. Yeah, Hooker's law. Yeah, like if you we have already talked about in NASA class, and then according to this equation, actually we can calculate the spring constant. Yeah, here the like displacement is 10 centimeter, which means 0.1 meter. I'm right. So which means k equal 20 n divide 0.n m, which means it is 200 n divide m. Yeah, it's just like this value. And then we know the spring constant and we know the m. Then we can calculate the frequency or the period. It's the same thing. For example, we calculate the frequency. Yeah, we just use this number to calculate, and it will around like 1 hertz. And then according to this frequency, we can calculate the period. So let's continue. Okay, I think this question is not, this problem is not difficult to understand. Am I right? If you have any question, just let me know. Okay, let's explore more things about pendulum motion. Okay, yeah, last class we have already talked about something about the pendulum motion, and here, uh, we have this like image to like learn like last week, and the restoring force is proportional to s. You can see here s. Actually, yeah. Firstly, let's review the tangential restoring force for a pendulum of length L displaced by arc length s is this one. These equations we have already try to know why this equation works. And do you remember that? And we use some like a small angle approximation. Yeah, did you? Yeah, and you can review the video and the like slides, NASA class, and you will know like this is the net force equations. And here L, the mg, the m is just this marble or ball, yeah, this object's quantity. quantity, so it's a fixed thing. And this gravity, like a acceleration. So this is also the fixed thing. The L is this line, this string's length. So it's also the fixed thing. So like this let force depend on this S, just this arc length. Yeah, which means like if you like observe a pendulum, and if the like L the L and M is just a fixed thing, and the net force is just depend on the arc length, and this is like a same linear restoring force as the spring, but with a constant MGL instead of K. You can see here X net T for the spring equal what? Negative K delta L. Am I right? So like the net for the spring is just depend on this K is a spring constant. It's a fixed thing. And this delta L is just like the displacement. And for the pendulum, like we just replace like the displacement like with arc length S. Yeah. So just like yeah, with the constant instead of K. So it's just like the similar form with a spring. Yeah, and this is a pendulum motion. And the oscillation of pendulum is simple. It's also a simple harmonic motion. The equation, since it is a simple harmonic motion, so we can use the sinusoidal function to represent it. And the equation of motion can be written for the arc length or the angle. It's just like this. Yeah. ST, yeah, it's just similar like the spring, the XT. If you remember like that, it is if you remember like the synthesis 40.1, like those equations, you will see the xt equal a cosine 2 pi ft. And here we just like replace st with st. The similar thing also like we can use the angle because you can see here for pendulum, the S will change and the angle theta will also change. So you can use this equation to represent ST, also the theta t. The theta t also have this this form, this like a change rule like that. Okay, and you can see here the uh, the like for so like for the like spring, do you know like we know the F equal over 2 pi km, am I right? And yeah, for the spring, for the like a pendulum, actually we just it's a similar thing. We just like replace K with mg divide L, which means for the like pendulum, the F should equal what? 1 over 2 pi, like mg divide L divide m, am I right? So here we just put equal 2 pi mg ml. So m will be removed. It will equal, it will just exactly this equation. Okay. So understand how this equation get, right? Yeah, let's do this again. For a spring, yeah, F equal what? Yeah, you need to remember this and it will help you to resolve many problems. 1 over 2 pi, like a square root K divide am I right? And for the like pendulum, we just like replace mgl like with replace the k with this one. So for the like pendulum frequency, it will be 2 pi mg L divide m 1 over mg L and then the L will be removed and 2 pi G L. Yeah, it's these things. Okay, from these things, like we can what we can know. Yeah, like the stronger gravity will increase the restoring force. This increases the frequency. Yeah, you can see if the gravity like goes up and the frequency will goes up. And if we increase in the length of the pendulum, it will decrease the frequency. You can see if we increase the length of pendulum, they will decrease the frequency. Am I right? So so we can know like sorry, we can know like for the like if the pendulum is short, the length of the pendulum is short and have a strong gravity, yeah, it will have a high frequency. And if it is the long pendulum and weak gravity, it will be a low frequency. Does it make sense to you? Yeah, this is for the pendulum. Okay, let's continue. Yeah. Uh, okay, I think I have already talked about this just now. The frequency can be obtained from the equation for the equation of mass on a spring by substituting mg divide L in place of k. Yeah, I have already talked about to tell you how we get this. Maybe let me do that again. Okay, that will help you to remember this. Yeah, and yeah, for the spring, F equal what? 1 over 2 pi root square k divide m. And then we just replace k with this mgl. So which means it mg L M. Okay, then you can see M will remove, and this inner thing it will equal G divided L. Yeah, just this equation. And the T is the obvious thing. You just like use 1 over frequency, it will be T. And okay, yeah, we have already talked about this. You can see if the gravity is strong and the frequency will increase. And if it's a length, if the like a pendulum length short, which means decrease, and the frequency will increase. And the opposite thing, if the gravity like decrease and the frequency will like lower, and the length of the pendulum increase and the frequency also lower. Yeah, does it make sense to you? Okay. Yeah, this is for the pendulum motion, and how to calculate the frequency for the pendulum motion. And just now, before we just focus on the spring frequency period. For now, we talk about the pendulum motion, like frequency pair and period frequency. And okay, let's try to observe this equation. And as for mass on spring, the frequency does not depend on the amplitude. We know about that F equal 1 over pi t k divide m. This is for the frequency for the mass on a spring. And the frequency, you can see, it just depends on the spring constant and the mass, but it does not depend on the amplitude. And if we observe this frequency, and actually also the period is independent of mass. You can see there is no mass here. Am I right? It just depends only on the length of the pendulum. You know, for in the Earth, the gravity is just the constant. Am I right? Unless you go to the Mars, other planets. Otherwise, in our Earth, the gravity will be same. So it in Earth, like it most depends on the length of the frequency for the pendulum. It depends on the length of the pendulum. Yeah, does it make sense to you? Yeah, it will not depend on the mass on like uh yeah, here it will not depend on this mass. Is it amazing? Amazing? It is interesting. Yeah, you can see the if you use a pendulum, like the how weight of this ball or things object connect with the pendulum. It doesn't matter. It just depend on the length of this pendulum. Okay, let's use some questions to let's see some questions. Yeah, try to understand more about that frequency and periodicity. Yeah, pendulum. Here is a quick check question, and a pendulum is pulled to the side. You can see, we just pull. Oh, sorry. Oh, sorry. We just pulled this pull this pendulum to this side, yeah, to this side, and released, and it will because of the force, yeah, and it will go down. The mass swings to the right as shown. The diagram shows position for half of the complete oscillation. Why it is half? Because it's just like a half period. One period is just A to B to C to E and E to D to C to back. This is one period, and this is just a period. Okay, the question is at which point our points is the speed the highest? At which point our points is the acceleration the greatest? At which point our points is the restoring force the greatest? Okay, I think it's not difficult. Am I right? So if the speed is the highest, which means it should be in the where? Equilibrium position. Am I right? So it should be what? C, I think. Yeah, does it make sense to you? Yeah, because in the equilibrium position and the speed is the highest. And you can see here, when you release it, and it has some potential energy, but there is no like a kinetic energy. Okay, at which point or points is the acceleration the greatest? Acceleration is great, which means, yeah, if we the acceleration is great, which means for this point equilibrium, the velocity is the highest. Am I right? So which means the acceleration is zero because it will not be not be faster. It will be slower, yeah, than this point if it goes on. So which point is acceleration the greatest? Yeah, it is the highest point. Yeah, so where? Okay, it is A and E. Am I right? And which point of the points is the restoring force the greatest? Restoring force is the greatest, which means it's the same with the acceleration thing. Yeah, because if there is the greatest a force and the acceleration will be the greatest. Does it make sense to you? To you? So it is still the AE. Does it make sense to you? Okay, yeah. This is the question. This is answers. Yeah, and this is similar with the spring. Yeah, and like we mentioned in class one, and all the simple harmonic motion, we can consider it as a it will be a spring a mass on spring like a motion oscillation, or it is a pendulum motion like a oscillation. Yeah. Okay. Let's see on the other question. A mass on the end of a spring is pulled to side and released. Yeah, here we just release it, and then you can see here it will. Oh, sorry. Why? Okay, it's just pull up here and release it, and it will go down, and this one is equilibrium position, and then goes to the right highest point, and then it will back. You can see here it will back to the equilibrium position here, and then go to the like this one and this one is the same position. Okay, the question is at which time our time showing is acceleration 0? At which time our time showing is kinetic energy a maximum? At which time our time showing is potential energy a maximum? Yeah, actually, at which time our time showing is acceleration 0, which means if the the speed reach to the highest and the acceleration will be 0 and then to the negative, it will be slow. Yeah, so which point? It should be equilibrium point. Am I right? So which should be, which one is equilibrium point? Yeah, B and D. Am I right? And which time or time showing is the kinetic energy. Kinetic energy, which means it has the like highest speed. Yeah, when the kinetic energy is the maximum. So it should be uh, okay. Yeah, it should be like the equilibrium point. Am I right? The position because you can see in the equilibrium position, the velocity is the highest. Yeah, does it make sense to you? Yeah, the kinetic energy is the maximum, and at which time or time shown is the potential energy a maximum. Yeah, which means the potential like there is no like a kinetic energy. It will be still like it will keep still like at this time and all the like a potential energy, which means should be the highest point. Yeah. So where is the highest point? It is ACE. Am I right? Yeah. ACE is also is like those three. Yeah, it's just a left highest point, right highest point, and left highest point. Does it make sense to you? Yeah. This is the answers for this question. Okay, let's see the other one. Like a ball on a massless, rigid rod oscillates as a simple pendulum with period of 2.0 seconds. If the ball is replaced with another ball having twice the mass, the period will be okay. It's yeah. This question is a little tricky, and here let's recall what is period equation. E equal what? Maybe you can write the F firstly, like a frequency. Frequency is 1 over 2 pi. What is it? Do you remember that? Gravity divided over L. So, and T, 1 over F, I'm right? So it is 2 pi or L divided G. So let's see that the period, does it dependent on like the mass? No. So which means the period will be what? Will be the same. Am I right? So the like right answer should be C. Does it make sense to you? Yeah. Okay. Let's see the other one. On planet, uh, on planet X, a ball on a massless, rigid rod oscillation at a simple pendulum like motion with a period of 2.0 seconds. If the pendulum is taken to the moon, like of plan X, like where the free ball acceleration g is half as big, the period will be. Okay, yeah, the same thing, the similar thing. Let's try to write what is the period 2 pi L G. Am I right? So here the pendulum is the same pendulum. Yeah, so the length will be the same thing. But here the gravity changed. Am I right? So like the moon of the planet X, like the free fall acceleration g is half as big, it half this thing, which means it is divided two, which means it will be two here. Am I right? So which means the new t should old t, this t. Am I right? So this is 1.41, blah, blah, blah. Then multiple 2, which means it is around 2.8. Does it make sense to you? So which means it should be D. Am I right? So yeah, we use this equation. And yeah, you can see it the like period related to the pendulum length and the gravity, and the gravity changed, and then the period changed. Okay, let's continue. Okay, let's see this question. A series of pendulums with different lengths, strings, and different masses is shown below. Each pendulum is pulled to the side by the same like small angel. The pendulum are released and they begin to swing from side to side. Okay, uh, okay, let's like put this question uh, like behind, and let's see why some questions just tell us like it's just about a small angel. Yeah, angle. So angle. Uh, do you remember when we like talk about the pendulum last class? We just use some small angle approximation to uh, uh, to get the net force. Do you remember that? If you don't remember, you can recall that part. Which means, if we want to use that equations, and uh, and there should be a small angle when you pull up the you pull up the mass. That makes sense to you. Otherwise, you cannot use the equation. Yeah, that equation is some kind ideal equation. So that's the reason why some question just adding this sentence, yeah, to clarify. Oh, you can use that equation. Okay, let's continue. The pendulums are released and they began to swing from side to side. Okay, the question is, which of the pendulum oscillates with the highest frequency? Okay, it's a similar thing. So we just write down the frequency equation. It's 1 over 2 pi g root square g over L. So here we just want to like a highest frequency, which means the G should be uh yeah, because it's in a like same plant, yeah, maybe earth, yeah, I guess. So it's the is the same thing. So we need to find the L, the smallest, and because we want to the highest. So the if the L is smallest, which means the F is highest. So which one is the smallest? Yeah, it's obvious. I'm right. It's A. Yeah, yeah. We just use this equation. Okay. Any question? If you have any question, yeah, you can now tell me now. So just let me know, like by email, by in my office hour. Yeah. Okay. Let's talk about the other question. Yeah, those questions are similar, but you can see it's just change some tiny things and it will change the results. Yeah, a series of pendulums with different length strings and different masses is shown below. Each pendulum is pulled to the side by the same angle. Yeah, it's yeah. Just try to remember why it's same small angle. The pendulum are released and they began to swing from side to side. And okay, the lowest here just ask you the lowest frequency. Oh, it's the same thing. 1 over 2 pi, yeah, and G divided L. If Lewis, which means the gravity will be small, but the gravity is the same thing, yeah, because they just do the lab like experiment in the same location, and so we just need to know the longest. We get the longest like length of pendulum. So I think it's obvious. I'm right. It is should be C. Okay. Yeah. Okay. Yeah. You can see we talk about a lot into this class, we talk about a lot about how to calculate the frequency and the period for like a spring and for the pendulum, which means yeah, this is important. Yeah. Okay, yeah, you can like sometimes when in some in many like area like in rural area you need to like sometimes you need to calculate some like because like I said the many like simple harmonic motion can be considered as like a like a pendulum motion or the spring motion. For example, the the heart beating. Yeah, it's just like a spring. Yeah, it's just a it's just like a left, right, left, right, left, right. It's just like a spring. So when you want to calculate uh the frequency for the heartbeat, yeah, you can see you just need to know some like a fixed like a constant like things, and then you can get the frequency and the period. And the frequency period for heart beating is very important. Like if you like learn some medical thing, and yeah, so which means the frequency and the period for a simple harmonic motion is very important. It decide the how the how fast the motion move. Yeah. Okay. Let's see the other example. Designing a pendulum for a clock. You can see a grandfather clock is designed so that one swing of pendulum in either direction takes 1 seconds. What is the length of pendulum? Okay. Let's see how to resolve those kind of questions. Okay, the period of pendulum depends only on its length according to the equation. In textbook. Yeah, actually, this is just this equation. I listed it here. Okay, one period of pendulum is two like swings. You can see, uh, like a, is designed so that one swing, like which is just from the highest left highest to the equilibrium position, and to the right highest. It's just like a half period. So the half period takes like 1 second, which means the full period is just 2 seconds. Am I right? Does it make sense to you? So then we use this equation. For now, we know the period, am I right? When we know the gravity acceleration, yeah, because it's in Earth. So then we can use these equations to get the length of the pendulum. Am I right? Yeah, just use it. It is just around like 1 meter. Then, and you can, if the length of pendulum is like a 0.993, and then the like period should be second, 2 seconds. Yeah. Okay. Let's access these things. Yeah, this is a father's like grandfather's a clock. It's a very old traditional style clock. I don't know if you can find those clock in some like a furniture store. Maybe it has already so old fashioned, but some people like it. Yeah. You can see a pendulum clock with a tick-out talk each second requires a long pendulum of about 1 meter. Yeah, you can see. Oh, sorry. I think I make a mistake. Let me move it. Okay. Yeah, you can see 1 meter, 1 meter. It's not short, am I right? It's quite long. So which means the grandfather like a clock should be higher, taller, should be higher than 1 meter. This is why this clock was originally known as tall kids clocks. You can see some like a clock is very tall because it need a uh, uh, because each second it requires a long pendulum like about 1 meter. Yeah, that makes sense to you. Okay. Let's try to, okay, actually, what I have already talked about in this today's class is the most important part, like how to calculate the frequency period for spring and for like for a pendulum. Yeah, this is the important, most important thing in today's class. And the left one is just like let you know about those things. And yeah, this is some like advanced knowledge, and you need to know that, and but you don't need to uh, mm, you need to pay attention. And I cannot say you don't need to pay attention. You need to know about that, but it's not that important than what we have already talked about. Okay, let's see the physical pendulums and locomotion. Yeah, a physical pendulum is a pendulum whose mass is distributed along its length. Yeah, I uh, yeah, you can see this is a simple pendulum. It's a small mass m at the end of a latch rod length, but the physical, yeah, you can see here. Yeah, a physical pendulum is an extended object with mass m and length L and a moment of inertia I. Yeah, so you can see the physical pendulum is kind of uh let me search it. Physical pendulum. Sorry. Yeah. I want to find a real like a example. Yeah, you can see if you hang this like a spring like a water spring in a hook, and if it moves in a like a small angle. It's just like a pendulum. Does it make sense to you? But it's not like the what we have already talked about. It's just like some physical pendulum. It has a long shape thing. Yeah, you can see it's a similar. It's there are so many examples, and you can see you can replace this like a bottle with different things, like some maybe some like rocks, maybe some bags. Yeah, some bags. Yeah, it's just like a real world pendulum thing like that. Okay, let's continue. So the position of the center of gravity of the physical pendulum is at a distance d from the pivot. You can see here. This is the pivot, and this is like the center of gravity. And the position of the center of gravity of the physical is at a distance d from this from the pivot. And okay, yeah, and the moment of inertial I is a measure of an object's resistance to rotation, increases the moment of inertia while keeping other variables equal, should cause the frequency to decrease. Yeah, you can see here. If you check the equation in this in textbook equation for 40.29, yeah, this is the equation for the like physical pendulum. Here is the moment of inertia. Okay, here is a D. Yeah, yeah, you can see because the object, the physical pendulum, usually they have weird shape. For example, the like some like weird thing, like some like bag, uh some toys, some, yeah, anything you can think about. It has some like a weird shape, and the center of gravity will be different, and the d will be different. Like the moment of inertial I with center distance, yeah, from the, yeah, the frequency can be determined by this one. So which means like if you increase the moment of inertia, and then the frequency, yeah, if you like increase this one, and the frequency will decrease. Uh, Does it make sense to you? Yeah, I think it is obvious. Am I right? So, like when the pendulum is posed to the pushed to the side, like here, it pushed to this side, a gravitational torque pulls it back. Yeah, because gravity is a gravity thing. Pulls it back. The greater the distance d of the center of gravity from the pivot point, the greater the torque. Increases this distance while keeping the other variable constant should cause the frequency to increase. Yeah, from this equation, you can see if you increase the distance, this distance from the center of gravity, it should increase the frequency. Yeah, doesn't make sense to you. Yeah. Okay, so like for physical pendulums, and the frequency is just this equation mgdi. Yeah, yeah, move, and then yeah, and you can see the frequency depends on the object's the mass, and the gravity thing is the same thing in on Earth. The D, yeah, you need to depend on D and the moment of inertia. Yeah. Okay. Let's keep talk about that. And there is one example, like finding the frequency of a swing leg. Yeah, a student in a biomechanic biomechanics lab, mechanics lab, measure the length of its leg from hip to heel to be like a 0.9 meter. What is the frequency of the pendulum motion of the student's leg? Like, what is the period? Actually, I think this is now like difficult. Yeah, this is just like a student's leg is just like a physical pendulum. Am I right? From the equation 4029, just this equation. Yeah, like we can like calculate we can calculate the like frequency if we know the like center of gravity distance d and the moment of inertia I. We will need to make some like simply assumption to estimate this length. We can model like a human leg reasonably well as a round of uniform cross section pivoted at one end, the hip. Recall from like chapter 7 that the moment of inertia of rod pivoted about its end is 1/3 ml. Yeah, actually the moment of inertia, this thing you need to like have already learned in chapter 7. If you don't know that, or if you don't know, or if you forgot that, you can review the chapter 7 to see what is this inertia. And the center of gravity of uniform length is at the midpoint, so the d should be half this value. So then we will put everything in this equation and we can get the frequency. Does this make sense to you? So you can see here is a leg. Okay, you can use the arm. If you like move the arm like a pendulum, you can also, yeah, the similar thing. Okay. Yeah, and then yeah, this is just continue to that one. Like we just put everything here. Oh, sorry. And then the period is 1/f. Okay, and let's try to access this. And notice that we didn't need to know the mass of the leg to find the period. Yeah, it doesn't relate to the like mass of the leg. The period of a physical pendulum does not depend on the mass, just as it doesn't for the simple pendulum. And the period depends only on the distribution of mass. When you swing your free leg forward to take another stride, correspond to half the period of this pendulum motion. For a period of 1.6 seconds, this is like a 0.8 seconds. For a normal working piece, one stride in just under 1 second sounds about right. Yeah, like you just one step, like it's just like a 0.8 second. Doesn't make sense to you. Yeah, it's if you work normal. Yeah, if you work like as a like a regular piece, it should be less than second. Yeah, you can try that. You can like try to click clock to like to see if this is right. Okay. Also, you can try it yourself. How do you hold your arms? You maintain your balance when working or running by moving your arms back and forth opposite the motion of your legs. You hold your arms so that the initial period of their motion matches that of your legs. Actually, if you when you run, when you work, and your legs and your like arms will swing at the same piece. At a normal walking piece, your arms are extended and naturally swing at the same period as your legs. When you run, your gait is more rapid. To decrease the period of the pendulum motion of your arms to match, you bend them at the elbows, like shortening their effective length and increasing the natural frequency of oscillation. To test this for yourself, try running fast with your arms fully extended. It's quite awkward. You can try that. Yeah, you will see. It's quite Yeah, it's quite weird. Okay, and okay, let's talk about the other the other thing, the other uh, term called damped oscillations. Actually, you can see we talk about the oscillations, the simple harmonic motions. It's just like I said, there is no, we assume there is no friction, but in the real world, there will be a friction. Yeah, for the pendulum or from for the spring, yeah, if there is a yeah spring, yeah, you can see as a glade run and the mass runs, and there will be a friction. And for the pendulum, yeah, there are some like air environment air like have some friction. Yeah, so this friction will make the oscillation that runs down and stop. We call it a damped oscillation. For pendulums, the main energy loss is air resistance or the drag force. The faster the motion, the bigger the drag force. As an oscillation decays, the rate of the decay decreases, and the difference between successive peaks is less. And you can see here, as like a oscillation decays, the rate of the decay decrease, and the difference between successive peak is less. You can see it will small. Yeah, at the beginning, it seems has a huge difference, but slowly it has the difference will be very small. Yeah, we call this damped oscillation. Actually, yeah, those most things we talk about in this chapter is just the ideal like oscillation. But in the real world, the damped oscillation is just the real world. But why we don't talk about this much? Yeah, because for the damped oscillation, you can see here, the main energy loss is air resistance, but it's just main. There are other like factors to affect the pendulum like move. So there are so many like things to affect that. So we don't we cannot like calculate in a mathematical form. That's the reason why we don't focus on that, because we cannot use a like a equation, mathematical equation to represent it. Okay, but you know this, and in the real world, it's just the oscillation will be damped. Okay. Yeah, the damped oscillation like causes X mass to decrease with time using this equation. Yeah, you can see. Oh, actually, this is also an ideal situation. Yeah, where E around 2.718. I think this is a Bayesian of nature like a logarithm, and A is initial amplitude. Yeah, this one I think you know about that. The standard decrease in X max is a exponential decay, and the constant tau is a time constant. Yeah, this is a time constant, and this X mass is a potential decline. You can see here exponential decline. Yeah, this is like a real world, like a damped oscillation thing. Okay, and there are different amounts of damping. Mathematically, the oscillation never like cases. However, the amplitude will be so small that is undetectable. Yeah, for practical purpose, the time constant tau is the lifetime of the oscillation, the measure of how long it takes to decay. Uh, if tau much smaller than t, the period, the oscillation persists over many periods, and the amplitude decrease is small. If the tau much bigger than period, the oscillation will damped quickly. Yeah, like here there are some like time constant. Yeah, this time constant will be determined by the environment, by the like the like real like this oscillation situation. And if this tau like smaller than the period, and the oscillation like will persist over many periods like this one. Yeah, but if the like tau much greater than the period, the oscillation will damped quickly. Yeah, this is like the damp situation. Yeah, here there is an example problem. 500 like a gram mass on a string oscillation as a pendulum. The pendulum energy decreases to 50% of its initial value in 30 seconds. What is the value of the damp constant? Yeah, actually, we just use this equation to resolve. Yeah, this kind of question. Yeah, the energy is proportional to the square of the amplitude. The energy decreases to 50% in seconds, so the amplitude decreases to uh, square root 0.5 equal around like a 0.71 of its initial value in seconds. So which means here, this one, the x max, like here the large difference in the head, the x max, like the difference, which should be equal this one. Like here is the t divided tau. Here is the seconds is the initial value t, and where tau is a time constant. So the negative 0.34 equal negative, yeah, gives the t equal, yeah, this one. Okay, does it make sense to you? Yeah, actually, I think you just use like this equation to try to calculate that one. Let's talk about the others, uh, like physical, uh, phenomenal, physical thing about the oscillations, like the driven oscillation and the resonance. And the driven oscillation is the motion of like an oscillator that is subject to a periodic external force. The initial frequency F0 of an oscillator is the frequency of the system if it is displaced from equilibrium and released. The driven frequency Fx is a periodic external force frequency. It is independent of the natural frequency. An oscillator's response curve is a graph of amplitude versus driven frequency. A resonance, you can see here, curve is a graph at the like just thus this is the oscillator's response curve. Yeah, it's a graphing of amplitude versus driven frequency. Yeah, how the driven frequency affect the amplitude for the oscillation from oscillation. Yeah, and a resonance is a large amplitude. Yeah, here a large amplitude response to a driven force whose frequency matches the natural frequency of the system. The natural frequency is often called the resonance frequency. Here, and you can see the driven oscillation like a situation, the oscillator has some specific frequency, like a move in a like a fixed period. For example, we talk about one example last class. There a tall building will like oscillate with a slight like angle because of the wind. Yeah, and if like the earthquake happens, like if the earthquake has a same has like a the the earthquake usually has a specific frequency, and it will affect the oscillation for this tall building. And if the earth's frequency is same with the tall buildings like a move frequency, and it will cause like a resonance, and this resonance will damage to this tall building very hugely. Yeah, this is a like a real world example for the driven oscillation and the resonance. Okay. Mm. And you can see the amplitude can become exceedingly large when the frequency match. Yeah. Here, a system with substantial damping has a much smaller response, you can see. But if special when there is a very little damping, and the lightly damping system has a very tall and very narrow response curve. A system with significant damping has a much smaller response. Yeah, you can see especially a damping like a oscillation. And when yeah, in the real world, this oscillation should be damping as a very small amplitude. But because of the driven oscillation, and if this driven oscillation has the same frequency with the original oscillator, and it will has a big amplitude. Yeah. For example, I don't know if you know this example, some bridge. Yeah, some bridge will move as a simple harmonic motion. Like it will move slightly every day in a specific frequency. Yeah, but if one troop passes from this bridge, and the troop work you can see it's usually like they work as a specific piece, and if this specific piece, which means the specific frequency, if this frequency is similar or the same with the frequency like this bridge oscillates, and it will cause a resonance, and then it will cause a big amplitude. It may break the bridge down. Yeah, this is an example in the real world. Okay, let's talk about the conceptual example, like fixing an unwanted resonance in a railroad car. Like a railroad cars has a natural frequency at which they rock side to side. Yeah. And they can lead to problems on certain stretches of track that have bumps where the rails join. If the joints alternate sides with a bump on the left rail and then on the right, a train car moving down the track is bumped one way and then the other. In some cases, bumps have caused rocking with amplitude large enough to derail the train. A train moving down the track at a certain speed is experience a large amplitude of oscillation due to alternating joints in the track. How can the driver correct this potential dangerous situation? Yeah, which means when the railroad cars, when it drive, it has a specific it will oscillate in a specific frequency, and in some there is some bumps cause rocking with amplitude large enough to derail the train. So how can drive correct this potential dangerous situation? Actually, the large amplitude oscillation is produced by a resonance matched between the frequency at which the train car rocks back and forth and the frequency at which the car hits a bump. Yeah, you can see the train car rocks back and forth, and then there is another frequency the car hits the bumps. To eliminate the resonance, the driver must either reduce the speed of the train, decreasing the driven frequency, or increase the speed of train, thus increase the driving frequency. Which means you cannot keep those two frequency same. You need to let them difference, or you just reduce the speed, or you increase the speed. Yeah. So it's perhaps surprising that increased speed of train could produce a smoother ride, but increased speed at which the train hits the bumps will eliminate the match with natural rocking frequency just as surely as decreasing the speed. Yeah, sometimes you may say, oh, increase the speed can make the train safer. Yeah, it doesn't matter. It doesn't make sense. Yeah, but the situation is that you cannot keep those two frequency at the same. You need to make a difference. Then you increase it or decrease it is also the solution. Does it make sense to you? Yeah. Okay. Let's see the other real world application resonance and hearing. Yeah, resonance in a system means that certain frequency produce a large response and others do not. Resonance enable frequency discrimination in the air. Like you can see here, this is the air drum, and this is some like a basilar membrane, and this is cochlear. And the sound waves enter this is how can we hear the sound? The, the sound wave like enter the air and cause the air drum to vibrate. Yeah, and the vibration in the air drum pass through a series small bones and to the cochlear, the sensor area of the inner like ear, where vibration in the fluid drive vibration in the basilar membrane. Yeah, so which means those can make this like the vibration. Yeah, and sorry, and so then like our like ear can hear the specific sound. Yeah, does it make sense to you? Okay. Like in a simplified model of the cochlear, sound waves produce large amplitude vibration of the basilar membrane and resonance. Lower frequency sound causes a response further from the stems. Hair cells sense the vibration and send signal to the brain. The fact that different frequencies produce maximal response at different positions allows your brain to very accurately determine frequency because a small shift in frequency causes a detectable change in the position of maximum response. Yeah, does this make sense to you? Yeah, we imagine the spiral structure of the cochlear enrolled with the basilar member separating two fluid filled chamber. The stapler, the nesting of the small bones, transfer vibrations into fluid in the cochlear. Yeah, here. Here, and as the distance from the steps increase, the membrane becomes wider and less stiff, so the resonance frequency decreases. Yeah, so which means that there is different like sounds of different frequency cause different response. Yeah, then we can hear different tone, different pitch like that. Okay, yeah, so this is what we learn in chapter 40 so far. And we mainly focus on the simple, simple harmonic motion and the how to what is it and how to describe it, how to analyze it, what's the energy on in during the simple harmonic motion and how to like calculate those things. Yeah, and the other thing is just some applications, some like related knowledge, and you need to know. And let's try to summarize it. Yeah. Okay. Yeah, there are some general principles and you need to know. Like the first one is the frequency and the period. Actually, the SHM, like simple harmonic motion, occurs when a linear restoring force acts to return a system to an equilibrium position. The frequency and the period depend on the details of the oscillator, but the frequency and period do not depend on the amplitude. We have already learned that the frequency, yeah, for the spring, yeah, it is what? It 1 over 2 pi km, right? And so the frequency for the pendulum it is 1 over 2 pi, like mgl, no, g, only g, yeah, it l, yeah. So it's just like the frequency, the period does not depend on the amplitude. Yeah, this is the net force for the spring, and this is the net force for the pendulum, and we have already talked about this is Hooker's law, and this we have already talked about how to get this. Like remember that smaller like approximate like angle. Yeah, okay. And this is about the frequency and period, and also yeah, the frequency and the period of a mass on a spring depend on the mass and the spring constant. They are the same for horizontal and vertical system. Yeah, this is for the spring, like no matter it is the horizontal and the vertical. And the frequency and the period of pendulum depend on the length and the free fall acceleration. They do not depend on the mass. You can see here. They just depend on the gravity acceleration and the length of the pendulum. It's not related to the mass or some yeah. Okay, let's see the other general principles. Energy. If there is no friction or dissipation, kinetic and potential energies are alternately transformed into each other in simple harmonic motion with the sum of two conceived. Yeah, we have learned that at the uh, yeah, those two has actually this total some energy is the constant value, and those two plus together is constant, and it will equal the maximum potential energy or the maximum uh, mm, kinetic energy. Does it make sense to you? We have already talked about this. And okay, so for the there is some important concepts for the oscillation. An oscillation is a repetitive motion about an equilibrium position. The amplitude A, yeah, is the maximum displaced from the equilibrium, and the period T is the time for one circle. We may also characterize an oscillation by its frequency f. Yeah, you can also use f to describe that. Yeah. Okay, this is how we describe an oscillation, the amplitude and period of the frequency. Okay, and for the simple harmonic, this is like a synthesis 40.1, and those equations are very important. Actually, most simple harmonic motion can displacement and the velocity and the acceleration, you can represent it using these equations. Yeah, it is described by a single function. Yeah. And this is just the position varies time and velocity varies time and accelerated varies time. Yeah, we have already talked about a lot. And okay, then we talk about some applications. Damping. Yeah, you can see in the real world. Yeah, simple harmonic motion with damping, due to drag, decrease in amplitude over time. The time constant tau determines how quickly the amplitude decreases. Yeah, so this is for the real world. Yeah, it usually damping, the oscillation with damping like that. And also we talk about resonance, a system that oscillates has a natural frequency of oscillation f0. Oscillance occurs if the system is driven with a frequency fx x that matches its natural frequency. This may produce a large here amplitude of oscillation. Yeah, I think you must met this situation before, when you hear some noise, it make your ear uncomfortable, which means there are some resonance. It just cause a very big amplitude. Yeah, does it make sense to you? Okay. There is also the other one application like physical pendulum. You can see we talk about a lot about the simple pendulum, but in the real world, a physical pendulum is most we will see it mostly. Yeah, now the simple pendulum. A physical pendulum is a pendulum with mass distributed along its length, and the frequency depends on the position of the center of gravity and the moment of inertia. Yeah, you can moment of inertia. You can review it in chapter 7. The motion of legs during walking can be described using a physical pendulum model. Yeah, this is how to calculate frequency for a physical pendulum. Yeah. Okay. Okay, yeah, this is today's class. So much thing, am I right? But just try to focus on like how to calculate the frequency, the period for the spring, the mass spring and the pendulum. And yeah, this is the most important in this class. Okay, hope you can, hope you understand what, hope I talk this clearly for you. If you have any like doubts or questions, just let me know or find me in the office hour. Okay, thank you. Bye.